Okay. So, how do we, any questions? Let's start with that. Any questions on how to perform these measurements? There are times when you can't measure the diameter. When does that happen? When are cases in which the diameter can't be measured? Some of you may have even seen this. If there's no inhibition, that represents a special case, right? So disc number 1 was our control. The bacteria grew right up to that disc. We do not, in those cases there, if there's growth up to the disc, we don't count the diameter of the disc, we just say it's 0. Okay? So in cases, I'm going to bet that for most of these, everybody would get that there's a measurement of 0 with that disc number 1. Okay, so in those cases, even though the disc itself may be 5 millimeters in diameter, there are no measurements 1 through 5 millimeters. It jumps straight to 6 or 7. It's about this first point which you can see some growth inhibition. So that represents one unique condition. When's the other time where we might see only, or where we might not be able to measure diameter? Alexi?
When the zone is still going, if it hits the edge of it and there's no growth because you don't know how far.
Yeah, so there were some plates where you had this spot, if this is your plate here, well, that's not a good spot, over here, you're saying it kind of maybe did that, or there were a couple where maybe you had another one with a much larger zone of inhibition and they overlapped with each other. You can't necessarily measure the diameter there. So what do we do in those cases? And think mathematically. Divide or, Taylor? Measure radius, multiply by 2. So in the case of measuring the radius, what we would want to do is go from the middle of that disc and measure outward to the best point we can find. And then multiply that by 2, and that gives us our zone of inhibition. So those are a couple of ways to get around it pretty darn easily. Who had a scenario like that where they had to, yeah, most of these I think had that. This just puts quantity to the results. And we can use this as a way to be more exact with our ranking. So for example, last time we just ranked by eye which one was the best, which one was the worst. If two have similar zones of inhibition that we can't distinguish by eye, sometimes measurement can help us with that decision. Where this becomes really important, though, is when we talk about antibiotics. And this is something that we will come back to later on, but when measuring zones of inhibition with antibiotics, it's a heavily controlled and standardized process. Because what we do to test them here has to be reproducible at Mercy, has to be reproducible at St. Mary's, other hospitals in Madison, other countries. And so there's a highly standardized process for testing growth. The other thing that has to be done in those cases too is that we have known bacteria that are either sensitive or resistant to those different antibiotics. And so you'll see when we talk about this with antibiotics, there are tables that we can use to say, hey, the zone of inhibition is X millimeters in diameter. That means that this bacteria is sensitive or resistant to this particular antibiotic. We can't do the same thing with chemicals necessarily. What we can do with chemicals is just say which one works better than the other. One more thing to recall, and I think that we kind of pointed this out when we compare, for example, 10% versus 30% bleach. What are some important factors that influence a chemical's ability to inhibit microbial growth? What the microbe is really important, absolutely. We saw, I think if I remember correctly, hydrogen peroxide worked best for most cases, but the least working one wasn't always the same for all cases. So the microbe can have a large influence. What else might be an influence? Temperature can be an influence, actually. Warmer temperatures seem to do better with helping chemicals achieve their activity than do colder temperatures. That does have an effect. Sometimes we can have combinatorial effects of 2 or 3 different chemicals or 2 or 3 different physical methods at the same time. You may hear the term hurdle method to describe this, where we're applying all the pressures at once. Another thing to think about is, what is the surface that you're using the chemical on? So for example, the chairs are incredibly porous. Most chemical treatments are probably not going to do really good at inhibiting the growth of microbes on our chairs. We may opt for a gas option. Okay. Or stainless steel. What does bleach do to stainless steel? It corrodes it. You never use bleach on stainless steel. And so that's kind of off topic, I suppose, but the type of surface that we have also is going to influence the chemicals that we choose. Okay. We ended up finishing our conversation on Monday by just saying that with the bacteria, with this method in bacteria, it tells us that how good a chemical is in relation to other chemicals, but it doesn't tell us what we call the minimal inhibitory concentration. What is a working description of minimal inhibitory concentration? What does that term actually mean? Emma?
Is it the minimum amount of chemical used to block?
Yeah, exactly. So it's the minimal amount of chemical that it takes to completely block growth of the microbe. Let's take a look at an example. So here is an example of a dilution experiment in which a chemical has been added in each of these tubes to different concentrations. Otherwise, everything else is the same. So the only variable in this experiment is the chemical. And let's say that this is, usually these are done in twofold dilutions. So let's say that this is something like 16% of the chemical, 8%, 4%, 2%, 1%, 0.5%, 0.25%, roughly. Okay? So typically these are done in twofold dilutions in comparison to the standard dilutions that, or the serial dilutions that we're doing for plate counts, which are typically tenfold. And we're looking for the minimal concentration. I have that backwards. I said that backwards. Damn it, I always do this every semester. Okay, other way. 16, 8, 4, 2, 1, half, 0.25. Every damn semester. Okay, sorry about that. Cross out the past minute, including the rant. As the concentration of chemical increases, obviously it should inhibit growth, or do better at inhibiting growth. We are looking for the minimal amount that, by eye, we observe no growth of the microorganism. So in this case here, if you were looking at this, you can start to see some fogginess in the tube at this point. This obviously is a black and white image. If it were colored, these would all be tan, and this would begin to look cloudy. We can measure this in different ways. Most often, these minimal inhibitory concentration experiments are done just by looking with our eye. Or we can use a spectrophotometer if we want something quantitative. But what we usually report is just the concentration. Okay? And again, there are things that can influence the concentration of the chemical that inhibits the growth. The type of microbe, the temperature that the incubation has occurred. Sometimes even the type of media that the bacteria are incubating in can have an effect on this minimal inhibitory concentration. One of the things that we should probably think about, though, is what's the relationship between this, a minimal inhibitory concentration, and a zone of inhibition? So as a chemical is, if a chemical is incredibly effective, meaning, let's say this. I don't want to draw this out. let's say that we have, and we find with B, that's not perfectly circular, and A. Which one works better at inhibiting growth? B, larger zone of inhibition. Which one would have then a smaller MIC, or smaller minimal inhibitory concentration? Yeah. So we said B works better at this concentration. Which of these two might we predict to have a smaller minimal inhibitory concentration? In other words, which one might it take less to inhibit the growth of the microbe? Think about this for a minute. And one of the things that I want you to remember about this is that the name of this experiment here, disk diffusion assay. What does that diffusion piece tell you about what's happening to the chemical as it's moving away from the disk? Okay? So take a minute to think about that. Again, which has the smaller MIC? Take like 2 minutes. Write something down for yourself. Concentration. Those who think A will have a smaller MIC. Okay. B. I don't know. Fair. I don't get it, Dan. Okay, good. That's a positive. All right. I'd have been fine with you raising your hand. All right. Let's take a look at this. And again, what I want to do here is kind of go through the theory of how these two correlate with each other. Disk diffusion. What is diffusion? Movement of a chemical from where to where? High to low concentrations. Where is the highest concentration of chemical A or B? In this experiment right here. Allison, what was that? On the disk, right? What happens to that concentration as we move away from the disk? Yeah. That concentration begins to decrease. Where this zone of inhibition, which is this distance here, what's happening at that interface, or that location right between where bacteria do and do not grow? What's true about the concentration of the chemical at that location? To the right of this line, it inhibited growth. To the left of the line, growth began to grow, or growth occurred. So what is that concentration by definition? What's that? Exactly. That's the MIC. That's the minimal inhibitory concentration that it takes to inhibit the growth of the microorganism. So let's make a couple of assumptions here. And these are good assumptions. Diffusion of chemical A and B from that point source, from the disk, is the same. They have the same gradient moving out from it. But we observe with A, imagine that we observe with A that the bacteria begin to grow closer to the disk. So which one would so I guess does this change anybody's answer? Well, this image up here. Obviously, I'm having a hard time with words today, so somebody explain this for me. B is the correct answer here. B requires less concentration to inhibit growth. How can we tell that from this experiment? I'll get you started. Chemical A and B are diffusing at the same rate. The bacteria grow closer to the disk around A, chemical A, than they do around chemical B. what does that mean about this? Is the concentration of chemical higher here for A, or is the concentration of B higher out here? Which one? A, yeah, higher for A. Therefore, it has a larger minimal inhibitory concentration. It would take more of it to inhibit the microbial growth. Takes less of chemical B to inhibit growth. Right. So there's what we would say is that there's an inverse correlation here, to summarize this. If we're comparing two chemicals with each other, the one that has a larger zone of inhibition, if these chemicals are applied on the disk at the same concentration, the one that has a larger zone of inhibition will have a smaller minimal inhibitory concentration. It takes less of that chemical to inhibit the growth of the microorganism. Questions on this concept? It's a pretty tricky one, so I want to make sure if there are any immediate questions to address them now. Okay. Let's take a look at some data. Let's actually go to something that maybe some of you actually do care about. Not implying you don't care about this, but let's talk about C. diff again. Yay! All right. Great start to the weekend. Wait, why can't we see it up here? Son of a gun. All right. There we go. Let's talk about C. diff. All right, here is an experiment. This one actually is an experiment in which they were looking at concentrations. And I feel like I'm going to have to explain something before we look at this in great detail. So the table here is reduction in Clostridium difficile spore counts on the hands of volunteers. Yes, people actually spread on their hands C. diff for this experiment, following chlorhexidine, gluconate, soap, and water wash, or use of alcohol-based hand rubs. So, just to orient you with this data real quick. Type of technique, Isogel, Endure, and Purell are all three forms of alcohol-based cleaning products, so what we would call hand sanitizers. Chlorhexidine, soap with a phenol or a bisphenol in it as well. What they're looking at here is the reduction in bacterial counts before and after. This is not an experiment of growth, but just a measurement of how much bacteria was there before the hand washing and afterward. So in this experiment, they took Taylor's hand. Taylor Blair, because I'm going to pick on you today. So they took your hand. Sorry. Oh, apparently I'm dialing a phone number. Okay. Took the hand, put C. diff all over it. Yay. Spores of C. diff. And then before, they took just a swab, swabbed an area, serial diluted, plated, counted how much bacteria there was. Okay, so we get a plate with lots of bacteria. Let's say 100. You washed your hands. Which would you like to wash with? Hand sanitizer or soap and water? Okay. You sure about that? Okay. We'll find out, I suppose. Like 11, roughly. This is roughly what we would say is a tenfold difference, or a 90% reduction. The way that they report this data in this particular table is on a log-based 10 scale. In other words, if you see a 1, that means there's 10 times less than there was before. If you see a 2, it means there was 100 times less than before. A log-based 10 scale is the same thing as saying 10 to the n, which n is the number that they report. So, take a look at the data here. Which one has the largest log reduction, or log change in the number of bacteria before and afterward? Taylor, which one? Have you chosen wisely? So what's the value for the washing with chlorhexidine? Ah, thank you for bringing that up. That's the p-value. That's a value of significance. So that's a statistical testing. Look at the one next to it. 0.9 plus or minus 0.37. They've done this numerous times. 0.9 is the average. 0.37 is kind of like those error bars of the standard deviation. Compare that to Isogel and Purell and Endure. Do these have greater decreases or less smaller decreases? Smaller. The values there are smaller. In other words, we saw a 0.9 log reduction, almost a 10-fold decrease when washing with soap and water. But when using Isogel, we saw a 0.1 log decrease, which really is like a representation of going from 100 cells to only like 90 afterwards. Or Endure, 0.37. That's like going from 100 down to 50 afterwards. So you have chosen wisely. Okay? Why do we see this observation? So that's the follow-up question. Why do we see this observation in this particular experiment? What's the true variable here? C. diff isn't a true variable, but we'll come back to that. What are they testing here? They're testing mechanisms of hand washing. Chlorhexidine, soap and water. Somebody describe to me the process by which you wash hands with soap and water. Please. Or I will force Jake to show you up. He's sitting in the back. He probably doesn't know, so God bless my life. Alana, how do we wash with soap and water?
Turn on the water, put warm water,
Okay.
put soap on your hands for 20 seconds,
Okay. And rinse. Okay, great. When using Purell hand sanitizer, what do? How does that process work? You're walking out of a hospital room, you spray some foam on your hands, what do? What's that, Emma? Okay, anything else? Okay. What's the difference in the process here? You could argue that length of time is different. Chemical is different too, right? What are some other differences? Okay, so what is the process of hand washing? If we were to describe, we use different terms like sterilization, disinfection, antiseptic, or degerming. Where does washing hands fit? Degerming. It's a physical removal of bacteria. And typically with hand sanitizers, we don't physically remove. What are we hoping for? What's the design? It's an antiseptic. The goal is to kill the bacteria that's already on your hands. What's true about C. diff, or what's true about how they did this experiment? Read the title to it. What's wrong with that, Grace? Spores. What in particular, with respect to this experiment, what do we know about spores? Not easily killed, Grace?
I was just saying they're really hard to get rid of.
Yeah, they're really hard to get rid of. What else? Dormant? Absolutely. 70% ethanol has no effect on spores whatsoever. None. Okay, so in order to remove spores, there are a couple of ways. One, stick your hands into an autoclave. Leave them there for 20 minutes and then take them out afterwards. That's option one. That seems a bit extreme though, right? Option two, probably much easier. Just wash them off. Allow them to go down the sink. What this brings up really is an idea of how do we... one we have to make smart choices about what we are using for removing bacteria or inhibiting bacterial growth based on the properties that we know about. C. diff is kind of in some ways a new problem. Maybe not for you guys, but for me, at least, this didn't really become a topic of conversation till about 10 years ago. And so at that time, hand sanitizers made a lot of sense because alcohol does work pretty well against Staph aureus and against Staph epi and E. coli and vancomycin-resistant enterococci and some other bacteria that we are particularly concerned about. But it doesn't work against spores. And so we have to think about what other practices could we use, or what practices might be better in order to reduce the microbial count. There's in my mind, there's an additional problem with hand sanitizers. And it comes down to things that we've talked about in terms of time of exposure and concentration. The concentration's high. 70% works really well. Actually, 70% ethanol works better than 95% because it doesn't evaporate as quickly. But the way that we put it onto our hands, it typically dries within a minute. Am I wrong on that? About a minute or so? And oftentimes, like I know me, when I put it on, I'm always like wringing out my hands afterwards because I hate the feel of it. So that reduces, like air drying them like this is going to reduce the amount of contact time as that ethanol is evaporating off. So these are factors that are going to influence, are the bacteria still there afterwards, or are they gone? Anybody have any questions on this figure or just this concept in general? So how do we decide that? How do we decide what chemicals to use? What I'll do is I'll give you guys a couple of minutes to think about that. So given what we talked about so far this week, really Monday and these 40 minutes today, and what we talked about a little bit last week as well, what are ways or things that we can do to determine what's going to be the most effective mechanism? Okay? And bring this personally. If you work in a nursing home and you want to know what's the best way to clean the bed sheets so that they are not soiled with bacteria afterwards after somebody has C. diff, which is a situation I know some people have been in, maybe not in this room though. Bring it to you personally, okay? How are you going to test, or how would you know which is the best mechanism? Right? Take a couple of minutes to kind of write out some thoughts.